Hello and welcome. Today we'll be applying the root locus analysis technique to design P, PI and PID controllers for a simple CISO process. But before we do that, let's construct the root locus for some standard transfer functions, some standard CISO processes. So here is the CISO loop. You have the control input, the output, the disturbance, the set point, and negative feedback of the output. Let's say we have a first order transfer function. For this first order transfer function, since the root, the open loop pole is s equal to minus 1 by tau. So this is the open loop pole, s equal to minus 1 by tau over here. And it will have one asymptote because there are no zeros. So there will be one root locus branch because the n, the order of the denominator of the open loop transfer function is 1. So there will be one branch, one asymptote, and because there is one asymptote, its angle is going to be minus 180 degrees. And does root locus exist here? Does root locus exist here? No, because the number of critical points, poles and zeros to the right is 0, which is not odd. Does root locus exist here? Yes, because the number of poles and zeros to the right is 1, which is odd, which is an odd number. And therefore root locus exists here, and that's your root locus plot right there. At kc equal to 0, s equal to minus 1 by tau is the root. As kc is increased, the closed loop characteristic equation root keeps moving this way. So that's the root locus for a first order lag. Now let's look at the root locus for a second order system, and we have the second order system over here. It has two real roots, s equal to minus 1 by tau 1 and minus 1 by tau 2. These are the two open loop roots, and if we apply a proportional controller kc, then second order system, no zeros, so you'll have two asymptotes. If you have two asymptotes, their angle is going to be plus minus 90 degrees. So the loci begin at, let's say tau 1 is greater than tau 2, so the loci begin here and ends up in two loci. What is the location of this breakpoint? You can get the breakpoint by applying the angle condition in the vicinity of the breakpoint. So if this distance is a, or you can actually get it by simply solving the quadratic, and it will turn out that this point is actually right in the middle between minus 1 by tau 2 and minus 1 by tau 1. So this guy, the breakpoint, is at s equal to half of minus 1 by tau 1 plus 1 by tau 2. You can get this by obtaining the quadratic roots of the closed loop characteristic equation and then invoking the condition Uh, Another way of getting this would be saying that okay, so here is another way of getting it. Uh, the real axis intercept of the asymptotes is going to be sum of the poles. Sum of the poles is minus 1 by tau 1 plus minus 1 by tau 2 divided by number of asymptotes. So number of asymptotes is actually 2. So therefore the real axis intercept of the asymptotes of the two asymptotes is at right in the middle, and therefore the root locus looks the way it looks as shown here. And you can see that a first order system or a second order system, the root locus never goes to the right half plane. First order system doesn't even show oscillations because the root is always real and negative. Second order system can show oscillations because you get, for sufficiently large Kc, you get complex conjugate roots. However, these complex conjugate roots never cross over into the right half plane, so first and second order systems under P control will always be stable and will never go unstable. However, please note that all real systems are third order or more, because any control system will have the process transfer function, the actuator, the control valve transfer function, and the sensor transfer function. So each one of them would be at least a lag, so any real process will be third order or more. So these two examples are, what shall we say, not really practical, just theoretical in nature. Now let's look at a third order where you got 3, and so it's a third order root locus. So you'll have 3 asymptotes because there are no zeros. These 3 asymptotes will be at an angle of plus minus 60 degree, and 3 times 180 divided by 3, that's 180 degrees. So here are the 3 asymptotes, you can see. And the real axis intercept of the asymptotes is going to be minus 1 by tau 1 sum of the poles, sum of the open loop poles, minus 1 by tau 2 minus 1 by tau 3 divided by total number of asymptotes, that's 3. And so you can see for the picture that is drawn there, I mean the asymptote looks like it's going to be somewhere over here, yeah, and so the asymptotes are going to be plus 60 degree, minus 60 degree, and then 180 degree, and therefore the root locus looks the way it does. The root locus begins from here and here and here. This ends up in the 180 degree asymptote, goes this way, there's a break point, and at the break point you break out into the complex plane, and then you turn around to reach the asymptotes. And you can see that there will be a gain for which you get sustained oscillations where you have purely imaginary roots, and if you crank up the gain further, then those roots move into the right half plane. These points and the gain corresponding to these 2 points can be obtained using complex algebra. Root array can be used, yeah. So that's the root locus for a third order system. You can also do a fourth order, fifth order system. It's just that the number of asymptotes will increase. Here is an interesting, so here we have a right half plane 0. So this is actually an inverse response transfer function, and alpha, tau 1, tau 2 are positive numbers, so minus alpha s plus 1. In this case, if you look at the so this is minus plus 1 by alpha, this is minus 1 by tau 1, and this is minus 1 by tau 2. If you look at the transfer function over here, you can see that this is not in standard form. So if you look at the characteristic equation, it is going to be 1 plus kc times gp, which is actually kc times minus alpha s plus 1 divided by the denominator. This is equal to 0, and if you solve this, what you are going to get is minus alpha s what you're going to get is minus alpha s plus 1 divided by the denominator is equal to minus 1 by kc. Now if you put it in standard pole 0 form, the standard pole 0 form is product s minus z's, s minus zeros divided by product of s minus poles. The standard form would actually be s minus 1 by alpha divided by s minus 1 by tau 1 into s minus 1 by tau 2, and I have taken minus alpha common in the numerator and tau 1 tau 2 common in the denominator, and therefore what you get from here is that the transfer function is actually in standard form. What the characteristic equation is s minus 1 by alpha divided by s minus 1 by tau 1 into s minus 1 by tau 2. This guy is not minus here, s plus, sorry, yeah, this is plus here. This guy is actually notice the minus alpha and the minus 1 by kc on the other side is actually cancel out, so plus tau 1 tau 2 by alpha kc. So now we are looking for those special points in the S plane for which the left hand side turns out to be a positive real number, not a negative real number, positive real number. And why this has happened is because of this right half plane 0 that creates an extra negative sign, and so the negative sign on the left hand side and the negative sign on the right hand side actually cancel out, and so what you get is g, the loop transfer function, must be equal to a positive real number, and therefore the angle condition for this example will be that the angle of g must be even multiple of pi, plus minus even multiple of pi. And therefore now with this knowledge, if you look at the root locus, let's start asking questions. Does the locus exist on this part? Obviously it's shown here, but why does it exist on this part? Because the number of critical points to the right is 0, which is even. So locus exists here. Does locus exist on this part? Number of points on the right is actually 1, corresponding to this 0. That is an odd number, and therefore locus does not exist here. Does locus exist between these two poles? Well, the number of critical points to the right is 1 pole here and 1 0 there. Total number is 2, and therefore that is an even number. So locus exists on this part. Does locus exist on this part? Well, the number of critical points to the right is odd, therefore locus actually does not exist. This is counterintuitive, but this has happened because of this negative sign, which caused a cancellation of the negative sign on the right hand side of the characteristic equation. Minus 1 by k became plus 1 by k, and so we are looking for those special points in the S plane that cause g to become a positive real number. And so locus is, so now now it's clear. As before, you will have asymptotes. So this is a net first order system, so the angle of the asymptote will be 0 degree. 0 degree means positive real axis. So that's your asymptote. So if you have to draw the root locus, if you just think about it, you start from locus exists on this part, so therefore as kc is increased above 0, this root moves that way, that root moves this way. There comes a breakpoint, and then if you increase kc further, you break out into the complex plane. The locus breaks out into the complex plane, and 0 acts as an attractor. So one of the branches, and in this it is shown as the lower branch, so one of the branches ends up at the 0, the other branch ends up on the 0 degree asymptote, and so that's your root locus. So when you apply the angle condition, if everything is in the left half plane, you use the rules that I discussed in the previous lecture. But if you have right half plane 0, then one will have to think it through and derive the angle condition, and then do what is following from that angle condition. So in this example, the angle condition is angle of G for a candidate S must be 0, 360 degrees, 0, 2 pi, 4 pi, 6 pi, 8 pi, plus minus odd multiple of plus minus even multiple of pi. Okay, and therefore the root locus turns out to be like this. Okay, here is another example of a third order system. This is a net third order system. Right? Oh, there is another pole that is very far away on this side, but which is not shown, and this example will be doing subsequently, so you'll see what I'm talking about. But there's a pole here, there's a pole here, there's a 0 here, and then there is a pole far away, not to scale. So you get 60 degree plus minus 60 degree asymptotes, 180 degree asymptote. So this would be the 180 degree asymptote. The 0 acts as an attractor, so it attracts locus over here, and you get the breakpoint. And because the 0 is an attractor, therefore you don't have locus going like this, you actually have locus going like that. And that also happens because if you calculate your asymptote intercept, real axis intercept of the asymptotes, that would be 0 plus whatever this number is, plus whatever this number is, plus whatever this number is, which is very far away, and therefore it would be a large magnitude number minus this guy divided by 3, and therefore the intercept actually turns out to be quite far away, perhaps here, perhaps there, I don't know. And then you do a 60-degree curve this way and a 60-degree curve that way, and because you break out and then the asymptote is actually quite far away, so therefore this asymptote acts as an attractor, and then you get this curvy behavior. Okay, and this curvy behavior is coming because of this 0 and the pole that is very far away. Okay, so these are some example root loci that can be drawn using the rules that we have seen previously. Now, how do we use root locus for designing controllers? So let's start with the simplest problem, designing a proportional controller. And we have, as usual, our process transfer function, and GP, what in this example that I'll be doing is actually 1 over s plus 1, 2s plus 1, 4s plus 1. And so you can see that open loop poles are s equal to minus 1, minus half, and minus 1 by 4. So the root locus shape would be, this is minus 1 by 4, this is minus half, and this is minus 1. So the root locus, as you can see, would be shaped like this. GC is equal to KC for a proportional controller, and mirror image. So that's your root locus right there. Sigma in this case is going to be minus 1, minus half, minus 1 by 4. So 1 3 by 4 divided by 3. So 1 3 by 4 divided by 3. That's going to be 4 1s are 4 plus 3 is 7. So 7 is so 7 by 12. How much is that? I don't know how much that is. निकालना पड़ेगा. So this is actually 7 about 0.6. So this is minus 0.5. So the real axis intercept is somewhere over there, and you'll get a line of 60 degree, and you'll get a line of minus 60 degree. These are your asymptotes, and that's your root locus. Now we want to design a controller for a closed loop damping coefficient of 0.5. A closed loop damping coefficient of 0.5 implies that the angle that is subtended by the dominant root cos phi, cos of that angle, and I'll call this angle phi, cos of phi should be equal to 0.5, which implies that phi is equal to 60 degree. And what that implies is that S is equal to minus A plus square root 3 AJ lies on the closed loop characteristic equation, and the closed loop characteristic equation is actually S plus 1 into 2S plus 1 into 4s plus 1 plus kc equal to 0. So that is actually 2s square plus 3s plus 1 into 4s plus 1 plus kc is equal to 0, and that becomes 8s cube 2s square plus 14 s square plus 3s plus 4s plus 7, that's 7s plus 1 plus kc is equal to 0. Now if you look at minus a plus square root 3 aj whole cube, that's going to be minus a cube plus 3 times plus 3 times uh-oh 3 times square root 3 a cube j minus plus or minus j square, so minus a, so this is well, let's see, plus 3 times minus a times square root 3 aj whole square. Square root 3a square, that will become a cube, there's a minus sign there, and j square is another minus, so that minus minus plus, so this is fine. And square root 3 square is 3, so this will be actually 3 multiplied by 3 a cube, and then we will get minus 3 a cube j. Okay, so minus 3 square root 3, and therefore this guy and this guy actually cancel out, and this is 3 3 is a 9, 9 a cube minus a cube, so that's actually 8 a cube. If you look at minus a plus square root 3 aj whole square, that's going to be a square minus 3 a square minus 2 a square minus 2 square root 3, no, minus 2 square root 3 aj, so that's going to be equal to minus 2 a square minus 2 square root 3 aj. And so if you put s equal to minus a plus square root 3 aj into the closed loop characteristic equation, then what you get is 8 times 8 a cube plus 14 times minus 2 a square minus 2 square root 3 a square j plus 7 into minus a minus square root 3 aj plus 1 plus kc is equal to 0. So that gives you 64 a cube minus 28 a square minus 28 square root 3 a square j minus 7a minus 7 plus 1 plus kc is equal to 0. And did I mess up a sign here? This is plus. Okay. And so the real part is 64a cube minus 28a square minus 7a plus 1 plus kc is equal to 0. No, so kc and the imaginary part is plus aj into 7 square root 3 minus 28 square root 3 a, and this must be equal to 0, so the imaginary part must be 0, so that gives a imaginary part equal to 0. Well, let's see. Imaginary part equal to 0 implies a is equal to 7 by 28, that is actually 1 by 4. So this particular root that has an angle 60 degrees is actually s equal to minus 1 by 4 plus minus square root 3 by 4 j. This is the dominant pole pair. Dominant pole pair. At this value of s, what is the kc? Because that's what we are interested in, what should be the proportional gain. You see, what we have actually is 1 plus kc gp is equal to 0, and therefore gp, because this point lies on the root locus, gp would be a negative real number, but kc must be a positive number. So what we have is kc is equal to minus 1 by gp, and that's how you get your kc. So I know what s is. Substitute this value of s into gp, because this number lies on the root locus, this would be a negative real number. Negative times negative is actually positive, and therefore that gives you kc. And because sometimes this s is slightly approximate, you may get a complex, very small magnitude complex part. To not get confused by that, it is better to say that kc is equal to 1 over mod of gp at s equal to dominant pole. And if you do that, what that gives is kc is equal to 1.5, and this comes from Kc is equal to 1 by magnitude of Gp at S equal to the dominant pole, and the dominant pole is minus 1 by 4 plus square root 3 by 4 J. That's how we get Kc equal to 1.5. So if we are going to do a P controller for a Kc of 1.5, we get dominant pole pairs for the closed loop characteristic equation that have a damping coefficient of 0.5. So this is P controller design using root locus. Now let us say that we are not happy with the P controller because the P controller results in steady state offset for a constant set point. If you change the set point from one value to another value and stay there, the closed loop response of the output will go towards the set point, but it never reaches there. There is always an offset. Now we are not happy with the offset, and so we decide that we are going to use a PI controller. So we will use design a PI controller, but before that I think the next slide summarizes what we just did in a very neat manner. So let me just go over that summary. So here's your CISO system. P controller means GC is equal to Kc. We want to obtain Kc such that closed loop damping coefficient is 5 for the dominant roots. Now for a damping coefficient of 0.5, S equal to minus A plus square root 3 Aj satisfies the closed loop characteristic equation, which turned out to be this. So if we substitute S in the closed S equal to minus A plus square root 3 Aj into the closed loop characteristic equation and do the algebra, we get a real part and a imaginary part should be equal to 0, and the imaginary part gives us A equal to 1 by 4. So S equal to minus 1 by 4 plus minus square root 3 by 4 J are the closed loop characteristic dominant poles, and for this dominant pole pair, Kc can be calculated as 1 over 1 by G, absolute value of that calculated at S equal to the dominant pole, and that gives us Kc is equal to 1.5. And if you look at the root locus is pretty standard. So this is minus 1 by 4, that's over here, yeah, minus 1 by 2, this is minus 1, yeah. Where is this breakpoint? How will we calculate this? The exact location of the breakpoint? Well, there's many ways. I will use the invocation of the angle condition in the vicinity of the breakpoint. So in the vicinity of the breakpoint, that means in the vicinity of the breakpoint, if I go a little bit above, an infinitesimal above that, and that infinitesimal above is delta, then because infinitesimally going above in the vicinity of the breakpoint, since that point must lie on the root locus, the change in angle in breaking out from the real axis into the complex plane in the vicinity of the breakpoint must be 0. So change in angle must be 0. So what that gives is, what does that give, man? Let's see, it will give angle subtended by this guy, angle subtended by this guy. No, this is a P controller, sorry, there's nothing over there. So angle subtended by this guy, angle subtended by that guy, and angle subtended by this guy. So let's say the distance between the minus half pole and the breakpoint is A. Then This angle is positive because counterclockwise, this is clockwise, so therefore what we will get is, let me call this phi 1, let me call this phi 2, and let me call this guy phi 3. So what that means is phi 1 plus phi 2 minus phi 3 must be equal to 0. And if I want to invoke this phi 1, so what is phi 1? Phi 1 is, how much is phi 1, man? Phi 1 would be delta over, what is the length from here to here to the breakpoint. So this is minus 1, this is minus half plus a. So delta divided by half plus a. Phi 2 will be plus delta over, going from over a, and phi 3 will be, the distance from here to here is 1 by 4 minus delta over, what shall we say, delta over 1 by 4 plus a. This should be equal to 0. So then we get a nonlinear equation in a, which is 1 over half plus a plus 1 over a minus 1 over 1 by 4 a should be equal to 0. Solve this for a, and you can use, for example, f0 to solve this for a. I don't know what the answer turns out to be, but maybe I'll do a quick calculation. So just give me 2 minutes to do that calculation, and I'll get back with the answer. So I'll just still the video for a little bit. So it turns out that when you solve this equation, a is equal to minus 0.1371, and therefore the breakpoint is uh, 0.5 minus kar do. So the breakpoint is actually, for this case, the breakpoint is s equal to minus 0.5 half plus 0.1371, and this guy turns out to be, अभी करके देख लो यार कितना होता है ये, 0.5 minus 1371, so 50001371, and I'll mess it up, but so this will be 9 minus 7 1, 9 minus 3 6, 4 minus 1, 4 में से एक गया, कितना हुआ भाई, 3. So S is equal to minus 0.3619, and you can actually substitute this value of S you can actually substitute this value of S in the closed loop characteristic equation, and also calculate the corresponding Kc. How do you calculate the corresponding Kc? Well, corresponding Kc is calculated by Kc at breakpoint will be equal to 1 over magnitude of Gp calculated at S equal to 0.36, S equal to minus 0.3619. There's no need for for this. Yeah, and if you do that, I don't know what the value comes out to be, but let me let's see what it turns out to be. I don't have that value, but you can calculate that value. So that's that P controller design. Now let's go to the next part of the problem. We are not happy with the P controller because it gives offset for a constant set point. So we say, okay, we'll do a PI controller. If you do a PI controller, then GP remains 1 over S plus 1 2s plus 1 into 4s plus 1, and GC is going to be Kc times tau I s plus 1 divided by tau I s. Question is, what should I set tau I as? And Kc is going to be adjusted so that the closed loop damping coefficient is 0.5. So what that means, whatever is the closed loop characteristic equation, S equal to minus A plus square root 3 AJ satisfies that characteristic equation. Now so in the design I have to choose tau I, and tau the integral action introduces 1 0 at s equal to minus 1 by minus 1 pole at s equal to 0 and 1 0 at s equal to minus 1 by tau I. So if I look at the loop transfer function, which is GPGC, if I look at the poles and zeros of the loop transfer functions, which is GPGC, so I've got a pole at the origin because of this chap, because of the integrator. Then I have a pole at 1, minus half and minus 4, so minus 1 by 4, so minus 1 by 4, minus half and minus 1, minus half, minus, so these are my poles. Now I have, as a designer, depending on what I choose tau I as, now you can see the rule of thumb is actually choose the tau I such that it cancels the dominant pole of the open loop transfer function. So the dominant pole, the slowest pole or the slowest time constant is actually 4. So I would like to cancel the pole corresponding to s equal to minus 1 by 4. This is the one that I'd like to cancel, and so what we then get is choose tau I is equal to 4 minutes. If I choose tau I is equal to 4 minutes, then the 0 will be right on top here, and so the pole 0 combination cancels out, and because it cancels out, I'll remove this, and once I have removed this, what are my poles and zeros? My poles and zeros are as shown there. The pole has cancelled the 0 has cancelled the pole at minus 1 by 4, and so my will look like this. So what is the gain that gives me a damping coefficient of 0.5, which implies angle phi is equal to 60 degree. We can proceed as we did for the P controller design, except that in this case now G, the loop transfer function with tau I is equal to 4 minutes, is going to be Kc divided by S times S plus 1 times 2s plus 1. 4s plus 1 cancels out, pole 0 pair cancels out, and therefore the by the way, this is 4s, and therefore the characteristic equation will turn out to be 1 plus g open loop equal to 0, and that will be 4s into s plus 1 into 2s plus 1 plus kc equal to 0, and so you will get 4s into 2s square plus 3s plus 1 plus kc is equal to 0, and this would become 8s cube plus 12s square plus 4s plus kc is equal to 0. So this is the closed loop characteristic equation. You substitute s equal to minus a plus square root 3aj into it, and so what you get is s cube will be 8a cube, so this will be 64a cube plus 12 into minus 2 minus 2 square root 3j times a square plus 4 into minus a plus square root 3aj plus kc equal to 0, and so what that gives you is 64a cube minus 24a square minus 4a plus kc, that's the real part, plus aj into 4 times square root 3 minus 24 times square root 3a equal to 0, and imaginary part equal to 0 gives me a is equal to 1 by 6. So the dominant root closed loop characteristic equation pole pair then is s equal to minus 1 by 6 plus minus square root 3 by 6 j. Notice that for a P controller we had the dominant pair as s equal to minus 1 by 4 plus minus square root 3 by 4j. So notice that this is actually moved rightwards. Earlier my real part was minus 1 by 4, now my real part is minus 1 by 6, which is smaller. Minus 1 by 4 is 0.2, 1 by 4 is 0.25, 1 by 6 is 0.166667. Yeah, so what this means is for the same underdamping or for the same damping coefficient, when you are using a PI controller, the gain that gives you a damping coefficient of 0.5 is actually, I wouldn't say the gain, the dominant pole for the same degree of oscillatoriness is more towards the right half plane. More towards the right half plane means the transients are slower. So a PI controller with an epsilon equal to or a damping coefficient equal to 0.5 will give a slower response compared to a P controller. Yeah. So that's that. At this S, what will Kc turn out to be? So Kc is going to be 1 over G open loop absolute value calculated at S equal to minus 1 by 6 plus square root 3 by 6 j, and if you do this you will see that Kc turns out to be 1.037037037, so we'll just say approximately equal to 1.04. This Kc is less than the Kc that we got for a P controller. For a P controller Kc for a P controller was 1.5. Kc for a Pi controller that we have gotten is 1.04. Now I'd like to comment a little bit about this choice of 4 minutes, or placing the 0 at the slowest open loop pole. To understand that, let me see, there is actually an open loop pole here at -1/4. There will be a pole at s equal to 0 because you have the integrator in a PI controller, and then there will be a 0 depending on what tau I choose. That 0, if that 0 is over here, what does that mean? That means tau I is large. As I keep making tau I smaller, this 0 keeps moving leftwards. Now think about this. If I choose my 0 to be extremely left, let's say over here, my choice, that means tau I is very large. Now that means tau I is very small. That means tau I is very small. If tau I is very small, that means I have a very aggressive integral action. And now you can see root locus would be of this kind. My breakpoint has moved between -1/4 and 0. Earlier the breakpoint was, I don't remember what it was, maybe it was, let's see, kitna tha bhaiya breakpoint? 0.3619. With a P controller the breakpoint was -0.3619. Now it will be between 0.25 and 0. It will be somewhere here. So the breakpoint will be more towards the right half plane, and your system will go unstable quicker at a lower gain. So your system, if you are using too small a tau I, your system goes unstable at too small a excuse me, proportional gain. Yeah, so this is not a good position. So we will not put it here. So we'll say, okay, if this is not a good position, let's, अरे यार क्या हो गया ये, let's move it that way. You will appreciate that for, even if I put it over here, locus will go this way. Of course the breakpoint may come a bit this way, but it is still less than 0.25. So for this breakpoint to be as far to the left as possible, the best option is that I place my pole, my 0, because of tau I on this guy, and because then this cancellation occurs, because then the cancellation has occurred, now my breakpoint will be somewhere over here, certainly more than 0.25 in terms of magnitude. So my root locus would be as left as possible, and the more left I am, the more away I am from the right half plane, the further away I am from instability, and that gives me faster closed loop dynamics, so that helps me. So for as fast as possible closed loop dynamics, this idea of locating the zero because of integral action, choosing tau I so that the zero cancels the slowest open loop pole, is a rule of thumb that is often used. Okay, so to summarize, we are using a PI controller and we want Kc such that closed loop damping coefficient is 0.5, and so we need to choose a reasonable value of tau I, and the rule of thumb is set tau I to the largest open loop time constant. Controller 0 then cancels open loop pole closest to the right half plane, and that helps move the locus leftwards, which stabilizes this, which helps the dynamics of the system, faster dynamics. So if you do the algebra, the closed loop characteristic equation turns out to be this, and if you substitute s equal to minus a plus square root 3 aj into the closed loop characteristic equation, you get this and that. And if you set the imaginary part equal to 0, the dominant pole pair is minus 1 6 plus minus square root 3 by 6j, and at this value of s, you get Kc as 1 by magnitude of g, where g is GCGP. Yeah, and the gain turns out to be, for a PI controller, that gives a closed loop damping coefficient of 0.5, is 1.037, which is less than what you got for a pure P controller. Okay, if you look at the root locus, well, that's what it looks like. Where is the break point? I leave that as an exercise for you to calculate. Here's another way of calculating it. So I just thought this right now. So this is your closed loop characteristic equation. For this closed loop characteristic equation, make the coefficient of the highest power of S1, so divide by 8, so we'll have S cube plus 12 by 8, which is 3 by 2 S square, plus 4 by 8, which is half S, plus Kc by 8 equal to 0. So this is your closed loop characteristic equation. For this characteristic equation, we want roots of this kind, S plus A whole square times S plus B, because at a break point you get repeated roots. This must be equal to 0. Okay. Oh, what the hell? Maybe I take the derivative of if I take the derivative of this guy, so it will be 3 S square. Yeah, because at the repeated root the derivative of the polynomial disappears. So let's take the derivative. So 3s square plus 3s plus half. This is the derivative of the polynomial, and at the repeated root this must go equal to 0, and this gives us a quadratic, and this quadratic can be solved to get the breakpoint coordinate as s equal to minus 3 by 6, 3 2 is 6, plus minus square root b square is 9, minus 4 3 half minus 6, divided by 3 2 is 6. So we'll get s equal to minus half plus or minus square root 3 by 6, whatever that turns out to be, you can calculate. This guy will be rejected because we want a root that is in this range. So we want minus half plus square root 3 by 6. How much is that? Whatever that is. So that's the breakpoint. So this is another way of calculating the breakpoint. But this technique will only work if the power of the characteristic equation is 3. If the power becomes 4, then you get a cubic. Getting the roots of a cubic. Of course, you can use MATLAB and get the roots. Okay, so but invoking the angle condition in the vicinity of the breakpoint, that's actually a more general technique which will work for any kind of transfer function of whatever order. Okay, now we say, well, PI controller response is actually too slow. You know, the dominant pole was, or the dominant roots of the closed loop characteristic equation were minus 1 by 6 plus minus square root 3 by 6j. This is too close to the right half plane and the closed loop response is too slow. If I increase the Kc further for a faster response, then the damping coefficient goes down and I get too much oscillatoriness. So I am not happy with the PI controller. I want faster dynamic characteristics. So we say, okay, let us design a PID controller using root locus, and now my specification is sorry. As before, GP is 1 over S plus 1 2S plus 1 4S plus 1, and GC, as before, we will use tau I is equal to 4 to cancel the dominant open loop pole, or the slowest time constant of the open loop transfer function. So GC will be Kc times tau d s plus 1 upon 4s times 0.1 tau d s plus 1. We want to know what should tau d be. How should we choose tau d so that when we set Kc for a closed loop damping coefficient of 0.5, the response is twice as fast as what we get for a PI controller. Like I said, for a PI controller the response was too slow. I said, oh, no, bhaiya, isko double speed karo iski. It should, if the rise time for a PI controller response is x minutes, I want the rise time with a PID controller to be x by 2 minutes, faster by 2 times. So if you want a faster response by 2 times, then S equal to 2 times the dominant pole of the PI controller, PI dominant pole, must lie on root locus. Now so in other words, we are saying S equal to the dominant pole for PI controller was minus 1 by 6 plus minus square root 3 by 6j. So S equal to minus 1 by 3 plus square root 3 by 3j must lie on root locus. So that's what we want. So we want to ensure that this particular point lies on the root locus, or the root locus passes through this particular point. So because we are talking of a very particular point, obviously the angle condition must be satisfied at this. Angle condition must be satisfied at S, at the desired S must be satisfied. So here's what I've done. This is the desired point through which the root locus must pass, this guy, and I would have chosen tau I to be 4 minutes. So tau I is as usual chosen to be 4 minutes, and therefore G open loop, which is equal to GCGP, would be Kc tau ds plus 1 divided by 4s into s plus 1 into 2s plus 1 into 0.1 tau ds plus 1. So that's G open loop. So it's got a 0 at minus 1 by tau d. That's this guy. It's got a pole at the origin. That's this guy. It's got a pole at s equal to minus half. That's because of this guy. It's got a pole at s equal to minus 1 because of this guy. And it's got a pole because of tau d, that is at minus 10 by tau d. That's this guy. Now look at these angles: phi 4, phi 3, psi 1, phi 2, phi 1. Obviously, if the locus is passing through the desired point, then the angle condition must be satisfied at that desired point. Poles subtend a negative angle because poles occur in the denominator of the transfer function. What is the other guy? Zeros subtend a positive angle because they occur in the numerator. So we'll follow this convention. So if poles subtend negative angles, this angle anyway is negative. So negative of negative is actually positive. So this would be phi 1 minus phi 2. This is a positive angle. Minus phi 3, that's this guy, minus phi 4, and 0 will subtend a positive angle, so this will be a positive angle, plus psi 1. This should be equal to, I don't know, plus 180 or minus 180. Choose one. We'll just say 180 degrees. Okay. Now what is phi 1? Phi 1 is actually magnitude of phi 1 is actually tan inverse, imaginary part is square root 3 by 3 divided by this distance is 1 by 3, which is actually tan inverse square root 3, which actually will be 60 degrees. Okay. Phi 2 would be tan inverse square root 3 by 3 to rahega, but what will be the, so phi 2 would be 1 by 2 minus 1 by 3, which is actually 1 by 6. Now whatever that is, calculate that. Phi 3 is equal to tan inverse square root 3 by 3 divided by, ये हाफ है, अभी ये कितना है, हाफ प्लस 1/6 नो, or so 2/3 ना, so this is 1/3 and that is 1, so that's actually 2/3. That's equal to whatever. So I did this calculation and which one is phi 1, which one is phi 2, I forget. 1/6, one is 73.9 degrees, so this is 73.9 degrees. What's the other guy? That's 40.9 degrees. So now if I substitute this into this equation, phi 2 plus phi 3 or phi 1 minus phi 2 minus phi 3 minus phi 2 minus phi 3, ये करो यार अब जरा, 73.9 प्लस 40.9 कितना होता भाई, 9 9 18, 1 4 7 4 11, ठीक है. So this is minus 114 and उसमें you are adding phi 1 and phi 1 is actually 60 degrees. How much is this? So this would be minus 0.8 minus 54.8 degrees. Yeah, and what? अब यार ये थोड़ा सा देखना पड़ेगा. Angle condition has to be invoked properly. So this is minus 54. Now angle because of the 0 is going to be tan inverse. Angle because of this guy is going to be plus tan inverse square root 3/3 divided by how much? 1/tau d minus half. An angle because of this pole will be minus tan inverse square root 3/3 divided by 10/tau d minus half. Okay, so I think it will be easier if we say that this angle, instead of we saying that it is minus 60 degree and therefore it became plus 60 degree, why don't we just say that this angle is minus 120 degrees? I think that is much easier. Or minus 120 degrees. Yeah, minus 120 degrees. So if we take this as minus 120 degrees, so so 73 plus 40 is 114.9 plus 120 is 234.8. So minus phi1 minus phi2 minus phi3 minus phi4 plus should be equal to this total angle should be minus 180 degrees. I think that's what we do. So yeah, so this guy is minus 234.8 degrees, and psi 1 minus phi 4 is written over here. So minus 234.8 degrees should be equal to minus 180 degrees. Okay, so this looks okay to me, and therefore then what we get is that tan inverse square root 3 by 3 over 1 by tau d minus half minus tan inverse square root 3 by 3 over 10 by tau d minus half. This should be equal to kitna? 54.8 degrees. And now this is a nonlinear equation that can be solved for tau d. Use S0 in MATLAB to do the solving, and what you get from there is tau d is equal to 1.5 minutes. And the remaining part is what should Kc be? Well, Kc can be calculated quite simply by invoking the magnitude condition, which is basically saying that Kc or magnitude of Kc is equal to 1 over magnitude of G open loop calculated at the dominant dominant closed loop pole, which here in this case is S equal to minus 1 by 3 plus square root 3 by 3j. And if you do the substitution and do the calculation right, you should get Kc is equal to 2.6963, which is approximately 2.7. And of course you got tau I is equal to 4 minutes. So this is what you have for a PID controller. Now I start becoming greedy and I say, bhai dekho, the other thing that I wanted to show in this part was, of course, yeah, the root locus. How would the root locus look? The root locus would look something like this. We've got S equal to 0, S equal to minus half, S equal to minus 1, and then I have a zero at S equal to minus 2 by 3, and at a pole at S equal to 20 by 3. So if you look at the sigma real axis intercept of this net third order system, that's going to be minus half, minus 1, minus 20 by 3 plus what is this guy? This is 2 by 3 plus 2 by 3, this whole thing divided by 3. So if you do this calculation, it will turn out that sigma is actually minus 2.5. So this is minus 1, this is minus half, So minus 2.5 will be further down there. So basically you got your 60-degree asymptotes coming out like that. You're going to get a break point. This is going to move this way, this is going to move that way, and then because you have to approach the asymptote and the asymptote is so far to the left, what happens is as the locus will break out and then it will go towards something like that. That's the way the root locus would look like. Question is, what is the break point? So if you want to calculate the break point, let's invoke the angle condition near in the vicinity of the break point. So what will we get? We'll get delta over, let me call this A, delta over half minus A minus no, sorry, delta over A that's this angle, there minus delta over half minus A, that's this angle. This is a 0 plus delta over, how much is this? ये 2/3 है, so 2/3 minus half plus A, so 1/6, 2/3 minus half, yeah, 1/6 plus A, that's this guy. ये पॉजिटिव होगा नेगेटिव होगा? अगर इसको पॉजिटिव ले रहे हो तो इसको नेगेटिव लेना पड़ेगा. ओके ओके, सो दिस विल बी नेगेटिव. And then there is this angle, this guy is going to be plus delta by half plus A. And then of course there's this guy, that's going to be plus delta over (20/3). ये क्या यार? 20/3 minus half plus A. This should be equal to 0. And so this guy turns out to be 1 by A minus 1 over half minus A minus 1 over 1 by 6 plus A plus 1 over half plus A. अरे यार ये क्या हुआ यार? Plus 1 over 37 by 6 plus A. 20 minus 3 is 37. Yeah. Should be equal to 0. Solve iteratively for A and you can then get A is equal to 0.2177, which gives S equal to minus 0.5 plus 0.2177 as the breakpoint, and that's actually minus 0.5. 2823 as your breakpoint. This is the breakpoint. At this breakpoint, Kc at breakpoint is going to be 1 over G calculated at S equal to minus 2823, and where G is GCGP, which is without the Kc in it. So G turns out to be, there has been a power outage, so I think this might just not get recorded. So G turns out to be, if you do all of that, so G would be S plus 1, 2S plus 1, 4S, 1.5S plus 1 divided by 0.15S plus 1. So that's G. And if you substitute S equal to minus 0.2823, calculate G and then take the inverse of that, that gives us Kc. So it turns out that Kc at the breakpoint is, how much is it? 0.5861. Breakpoint. Okay. So this is PID controller design. Now just to summarize, this is your PID controller. We want a response speed that is twice of the PI controller, and we want a closed loop damping coefficient as before of 0.5. So set tau I is equal to the largest open loop time constant. For twice the response speed of a PI controller, the dominant pole pair should be twice the magnitude of the, twice the PI dominant pair. And so the dominant pole pair is this, where this is the dominant PI controller pole pair. So S equal to minus 1 by 3 plus minus square root 3 by 3j must satisfy the angle condition to be on the root locus. And we put in the angle condition, and from that angle condition you basically get this equation, and this equation implies tau d is equal to 1.5 minutes, and Kc turns out to be 2.7 by invoking the, this is called the magnitude condition. And if you look at the root locus, you can particularly see that the point minus 1 by 3 square root 3 by 3 lies on the root locus. That is because we chose tau d to force the locus to pass through this point. Okay, we are greedy people, so we say, well, this is not good enough. I want the response to be twice as fast as a P controller response. You know, in the P controller response, so I want twice as fast as P controller, and P controller was faster than the PI controller, because if you remember, P controller dominant pair was S equal to minus 1 by 4 plus square root 3 by 4j. So I want a response that is twice as fast as the P controller, and so we'll say we want S equal to minus 1 by 2 plus square root 3 by 2j to lie on the root locus. So this point, if it lies on the root locus, it will be twice as fast as the P controller dominant pole pair, and epsilon will also be 0.5 as desired. So again we will have to invoke the angle condition, and one can see, okay, let me try a PID controller. If I try a PID controller, then what will happen is, if I try a PID controller, s equal to 0 पे है, s equal to minus half, s equal to minus 1. Now this is minus half. So what I want is this point to lie on the PID controller. So let us say now if I put a tau d, okay, this angle is 60 degree. This angle is 60 degree because this is minus 1 and this is square root 3 by 2. Real axis, imaginary axis. Now the pole here will put in an angle of minus 90. So minus 90, minus 60, and so this is minus 120. So minus 90, minus 60, minus 120. So plus the angle due to the 0 that I put in, plus the angle due to the pole which is 10 times away from the 0, because in the derivative I'm putting tau ds plus 1 divided by 0.1 tau ds plus 1. So the pole that I get will be s equal to 10 by tau d, so that is 10 times as far away as the 0 corresponding to s equal to minus 1 by tau d. This should be minus 180 degrees. If this should be minus 180 degrees, this is anyway minus 180 degrees, so ye cut gaya. So this would be minus. So what we have is psi minus phi should be equal to 90 degrees. Now you can see, if I choose a pole, a 0 location that is over here, then pole will be somewhere over here, 10 times the distance. This angle is less than 90. So there is no way you can have this equation satisfied if you choose a tau d over here. If I choose a tau d over here, the angle because of that would be 90 degrees, but the angle because of this would be some negative number, and so the net angle will be minus 85, minus 80, but not, or so you will get to 85, 80, 81, 82, 83, 84, 85, but not 90, because this guy will be contributing a negative angle. Now if I start putting my 0 over here, I am contributing a more than 90 degree angle because of the 0. But if this guy is 10 times the distance, you see this angle is also increasing. As the 0 is moving this way, the pole is also moving this way, because the pole is only 10 times the distance away. And so what happens is the contribution of this angle also, phi also starts to increase. So it turns out that if you put a PID controller, the angle condition cannot be satisfied unless you do 0.01 tau d, take the pole very, very far away. But those kinds of circuits are much more expensive. Electrical circuits that implement this kind of a lead lag, they are typically standard, and they'll have numerator time constant as tau d and the denominator time constant as 0.1 tau d, not 0.05 or 0.01 tau d, and therefore using a single derivative lead lag, it is very difficult to satisfy the angle condition. In fact, if you take this as the form of the derivative lead lag, you cannot satisfy this angle condition, and so a PID controller cannot give you this kind of performance. So if PID cannot give this kind of performance, well, we'll do PIDD, we'll do double derivative, दो लगा देंगे. So if I say okay, अभी 2 लगा देंगे, then sorry, ये क्या हुआ यार, keep, oh shucks, I made a mistake. So कुछ, because there is no power right now, what are we doing, man? Slideshow. Okay, so this is where we were. So now we will say GC is actually KC times 4s plus 1 divided by 4s, that's the pi part. The derivative part or double derivative part is tau ds plus 1 divided by 0.1 tau ds plus 1 whole square, because you cannot put two of them. And of course this guy will cancel the GP pole at s equal to minus 1 by 4. So now the angle condition would be, this angle is 60 degrees, this angle is minus 120 degrees, so minus 60 minus 120, the one at minus half will put in an angle of minus 90 degrees. Okay, and your pole will put in an angle of your 0, because of there are two zeros, so the angle would be 2 times psi, and the angle because of the pole corresponding to this will be minus 2 times phi, and net angle should be minus 180. And what this does is ye और ये cancel हो गया, and so what you get is psi minus phi should be equal to 45 degree, and psi will be the angle of the 0, that is going to be tan inverse square root 3 by 2 divided by 1 by tau d minus half. And phi is going to be tan inverse square root 3 by 2 10 by tau d minus half. And so what we have is tan inverse square root 3 by 2 divided by 1 by tau d minus half minus tan inverse square root 3 by 2 by 10 by tau d minus half. This should be equal to 45 degrees. This is an equation that can be solved. So you solve it for tau d, and what that does is it gives a tau d of 0.8 minutes. And corresponding to this tau d of 0.8 minutes, if you include the angle condition, sorry, the magnitude condition, if you invoke the magnitude condition and say, well, Kc is equal to 1 by G open loop calculated at S equal to whatever was the dominant pole that we were forcing, which was minus 1 by 2 plus square root 3 by 2j. If you do this calculation, this guy turns out to be how much? Let me see. 7 point something if I remember correctly. I have lost the paper. कहाँ गया यार? हाँ, 7.64. So thus we have Kc, we have tau d, and we have tau I is equal to 4 minutes. And our controller has been designed. You can repeat similar to what we did for a PID controller. For the PIDD controller, one can invoke the angle condition for the. By the way, so let's discuss what the root locus would look like. And so if I look at the root locus, what do I have? I've got s equal to 0, s equal to minus half, s is equal to minus 1, and tau d is 0.8, so s equal to 1.25, minus 1.25, there is a 0. And 10 times of that somewhere over here at 12.5, minus 12.5, there is a pole. And so, and this is repeated twice, and this is repeated twice. So if you look at the real intercept of the asymptotes, that is going to be minus half, minus 1, minus 12.5 into 2, because it's done twice, plus 1.25 into 2 divided by 3, and this guy, if you calculate, it turns out to be, let me see, it turns out to be minus 8 actually. So the asymptote is actually somewhere, I don't know, quite far away, somewhere over here. And you got the asymptote at minus 60 plus 60. So yeah, so you'll get the root locus like this. There will be a break point, but then it must go towards the asymptote, you know. So actually you will have something like this. That's what the root locus would look like. Quite curved the root locus would look like. And if you invoke the angle condition at the breakpoint, then what you will have is, let us call this A, then delta by A, that's this angle, minus delta by half minus A, plus delta by half plus A, minus delta by 1.25 minus half plus A. 1.25 minus half is 0.75, so 0.75 plus A. That's because of this guy. But then this has to be done twice because it is repeated twice, and then the last guy is going to be 2 delta last guy is going to be plus so 2 delta divided by 12.5 minus half, so that's actually 12. plus A, and that's equal to 0. Solve for A, and it turns out that A for this guy is 0.2342, and at this, so therefore that gives S is equal to minus half plus 0.2342. So the breakpoint is actually S is equal to minus 0.2658. This is the breakpoint. And Kc turns out to be 1 by G open loop magnitude calculated at S is equal to minus 0.2658, and if you do the necessary calculations, this turns out to be 0.56, 0.50 at the breakpoint. Kc at the breakpoint. So to summarize, Gp is the same as before. Closed loop characteristic equation damping coefficient desired is 0.5. I want a response speed that is twice that of a P controller. So as before, we set tau I is equal to 4 minutes. The dominant pole pair should be twice the P dominant pair, and therefore S equal to minus half plus minus square root 3 by 2j must satisfy the angle condition to be on the root locus. As we discussed, a single lead lag cannot cause the angle condition to be satisfied, a single lead lag of this form, and so we decided to put in two identical lead lags, and so GC turned out to be this, and then we invoked the angle condition to force the locus, root locus, to pass through minus half square root 3 by 2, to force it to pass through this point, and upon invoking the angle condition we got tau d is equal to 0.8 minutes, and on invoking the magnitude condition we got Kc is equal to 7.64, and that's that. If you look at the root locus, you see the root locus is bent over so much, and that is because the asymptotes are so far to the left. But the key point is that it is passing through the desired point. Well, that's that. What I did then later on was simulated the dynamic response for the controller tunings that I have obtained, and this is what it is. This is the P controller, PI, PID, PI double D, and you can see that PID is much faster than PI and PIDD is much faster than P, and this quickening of the response is happening because of deliberate designed placement of lead lags that alter the dynamic response appropriately. So this is all that I had to tell you, and this brings us to the end of this lecture. To summarize what we have seen, the procedure is very simple. The first thing you need to do is obtain desired closed loop pole location. If you don't have any such specification, how fast should it be, how slow should it be, then you just put a P controller. If you want no offset, just design a PI controller and choose tau I to cancel the dominant open loop pole. If there are specifications of the degree of oscillatoriness, that means the closed loop damping coefficient or the speed of response, then you are indirectly saying that the root locus must pass through such and such point. So if you have that the root locus must pass through such and such a point, then the first thing you do is set tau I to cancel the slowest open loop pole for 0 offset, and then you choose the lead lag tau d to force the locus to pass through the desired closed loop pole. Angle condition would give the necessary tau d, magnitude condition gives the necessary kc, and of course you should put in this lead lag if and only if a simple PI controller does not give a fast enough closed loop response and you want the response to be speeded up significantly. The derivative in the lead lag, the derivative lead lag is used to pull the root locus sufficiently to the left, and this pulling of the locus to the left actually gives a faster response. If you want the response to be quickened to a very large degree, then a single derivative lead lag may not suffice, in which case you may have to use a double derivative. But please note that whenever you apply a lead lag where the lead time constant is much larger, the numerator time constant is much larger than the denominator time constant, you actually end up amplifying noise. So that's the flip side of putting in these lead lags. And in all of this, I hope you realize that the root locus construction rules are very important because they allow us to easily visualize how the root locus would get reshaped if I place a 0 here or a 0 there and so on and so forth. So where to place the 0 corresponding to the integral action or the derivative action, that can easily be visualized by invoking the root locus construction rules and seeing how these rules reshape the root locus depending on where the 0 is placed. Okay, so that's why we covered these root locus construction rules. And with this I come to the end of this rather very long lecture, but these two lectures, the previous one and this one, complete whatever I wanted to do with root locus. Next time onwards we will look at advanced control systems, advanced control structures, cascade control, feed forward feedback control, ratio control, override control, and things like that. And then we will move on to frequency domain analysis, which may take another 2 weeks. Okay, so that's that. Thank you for your attention and thank you for patiently going through this. Thanks again, and goodbye. It's a 2-hour lecture. I can't believe this, man.